In this video, I want to talk to you about working with a small sample test for a single population mean. We've been through a large sample test before, and we saw that there were 4 steps that we follow to conduct a test hypothesis. That's not going to change. What changes when you move from large to small samples is that the sampling distribution that you work with has to adjust. The normal distribution, the Z distribution that we use for large samples, is inappropriate to use when you have small samples. And let's get this out of the way right away. What is a large, what is a small sample? That question is a really good one to ask yourself whenever you're doing any kind of analysis. What is it? Is this a large sample? And if not, does it qualify for a small sample? And the answer to those questions depends a lot on what you're doing. So far, really, we've only taken a look at working with means and working with proportions. Now, we haven't done a test for population proportion, but that's coming soon. What we saw when we did confidence intervals for means is that if you had 30 or more, we generally considered that a large sample confidence interval, and if it was less than 30, we considered that a small sample confidence interval. That same 30 or more works for means as well when you're doing a test of hypothesis. So the confidence interval, the test, large sample, small sample, when you're working with means, 30 or more large, less than 30 small. We saw how when we have a large sample, the central limit theorem guarantees us the results and there's not a lot of risk involved. However, when you're working with small samples, like I'm going to be talking about here, that's only going to work if the population that you're sampling from is approximately normal. All right, so that's a sample size issue. The last thing I'll say about that before I move on, when we move to proportions, there's still a sample size issue. It's just that 30 or more doesn't work with proportions, and I'll save the rest of that conversation for later. So we have a small sample now, a sample less than 30, and we want to do a test hypothesis for the population mean. What you see on the screen right now, step 1, formulate the test. The parameter is equal to hypothesized value. We're going to say mu is equal to some mu naught, some specific value. The alternative might be mu is not equal to. It might be mu is less than that value. It might be mu is greater than. The same 3 choices that you have when you're working with a large sample test apply to a small sample as well. So the null and the alternative really doesn't change. The form of the test statistic doesn't change either. We're going to take statistics that we find from our sample, we're going to put them together, we're going to take, and there actually should be, and I don't see it here, this should be x bar. Take the sample mean minus the hypothesized value of mu divided by sigma over the square root of n. This is going to be some number on a printout. I never want you to have to go through the calculations. The software's come a long way. Gosh, I remember the days when we had to do the math by hand, but no more. So we're going to be getting test statistics off of printouts, and now you need to evaluate that. And as we've seen before, evaluating the test statistic, there's a couple different techniques. There's the rejection region method, and rejection region states value of the test statistic that are unexpected and lead us to reject H naught. An example of which, if you have an alpha equal 0.10 and you're doing a two-tailed test, well, we're going to see an example like this in a second. When you have a two-tailed test, you got to take that alpha of 0.10 and split it into 2 different 0.05s. One of those 0.05s you put in the lower tail, one of those 0.05s you put in the upper tail of, in this case, it's going to be a t distribution. If the sample size was 15, it'd be 14 degrees of freedom. We're going to go to a table, and I'm going to do an example where I pull the table in, but this is what the rejection region would look like. And this symbol here should be a T as well. Wow, did not get through my editor there. I am my editor, so I'm going to blame myself on this. So it should be T is greater than 1.761 or T is less than negative 1.761. If you're doing a two-tailed test, you have a two-sided rejection region. If you're doing a one-tailed test, you're going to have a one-sided rejection region. So you're going to have to be up to speed with finding rejection regions. The other way of making a conclusion in a test hypothesis is to use the p-value approach. And the p-value, I just had this conversation with you probably in the previous lecture, the p-value gives us the probability of observing a test statistic even further out there in the tail than the one you observed. Finding p-values was something I talked to you about, and I'm going to ask you to find p-values, but only in a large sample case, working with a normal distribution, working with the normal inverse function, or I guess the normal distribution function would be appropriate when you're working with p-values. If you're working with a t-distribution, when you're working with small samples, I'm just going to make the blanket statement. If I ask you to work with p-values, I'll provide those on a printout or some kind of template that I've created for you. So you're going to have to find the p-value. So evaluating a test statistic, we have rejection regions, we have p-values, and then we make conclusions. And your conclusions, if you're using rejection regions, we've seen before, it's the same approach now. We compare test statistics to rejection regions to decide if H naught should be rejected. If you're working with p-values, we compare the p-value to alpha. We saw before, when p is low, we reject the null hypothesis. When p is high, we fail to reject. And so outside of us changing to a different distribution here, instead of working with large samples, when we go with small samples, we got to work with the t-distribution. Everything's pretty much the same. Again, that t-distribution comes with an extra assumption. We need the population that we're sampling from to be approximately normal. But the technique itself, and this is from my side of the microphone, it's just a test hypothesis. And I know you're still early in the game with your test hypothesis, and that's fair. But you're going to come to learn that there's this test hypothesis technique that we just have a whole bunch of applications for. So let's take a look at an example. And the example I want to take a look at, before I do that, almost missed. This is what rejection regions look like. At alpha equal 0.05, and perhaps I should have used 0.10 because that was what I used in the rejection region. But at some level of alpha, this alpha value should be between 0.01, 99% confident, and 0.10, 90% confident. You're either going to reject or fail to reject the null hypothesis. Ooh, excuse me. Either reject or fail to reject the null hypothesis. If you reject, there's sufficient evidence to indicate that the alternative is true. If you fail to reject, there's insufficient evidence to indicate that the alternative is true. And whenever you give me conclusions in a test hypothesis, this part here, HA is true, I want you to tell me what that means in the context of the example. There's sufficient evidence to indicate that the mean time watching or pumping gas at a gas station is less than 5 minutes. I think that was an example I've done previously. There's sufficient evidence to indicate that the proportion of all students with a college tattoo exceeds 25%. That might be something we see when we work with proportions. There's sufficient evidence to indicate that there is a positive linear relationship between the size of a house and the price of a house. That might be a regression, a simple linear regression type of conclusion in a test. The point is, you say your alpha, you say your decision, we reject, we fail to reject, but then you tell me what that means in the words of the problem. All right, so now let's take a look at our example. A landscaping business estimates their labor costs based on the number of plantings of trees, shrubs, etc. for a particular job. For cost estimating purposes, we're just going to look at one particular type of job. Managers use 2 hours of labor time for the planting of a medium-sized tree. That's what they guess. If you say, all right, I got 5 medium-sized trees, that's 10 hours. 10 medium-sized trees, that's 20 hours. Each one is a 2-hour estimate. Actual times from a sample of 10 plantings, there's your small sample, right, during the past month in hours are shown here. So the first job, we were planting a single medium-sized tree, and we can see that the first estimate, or the first time, was actually 1.7 hours, obviously less than 2. The second one was 1.5, then 2.6, then 2.2, and you can see all 10 of them here. Those are actual times of planting a single medium-sized tree. We want to conduct a test to determine if the mean tree planting time for all medium-sized trees, that's mu, if you average these 10 values here, that'd be an X bar, that'd be a sample mean. We want to determine if mu differs from 2 hours, and I'm asking you to use, or I'm telling you to use an alpha of 0.10. So the first step is to come up, what is a test? What are we trying to say? We're trying to say the mean of all, we're trying to say mu differs from 2. There's your alternative hypothesis right there. And so we write that as our alternative. By default, the null hypothesis becomes mu is equal to 2. If I wanted to test to see if the average exceeds 2, we do a greater than test. If I wanted to see if the average is less than 3 hours, we do a less than test. Here I want to test to see if the average of all differs from 2. And so now I need to go and put this data into a spreadsheet and come up with a printout. And here is a little template I prepared for you that you have access to. This is using the unknown standard deviation test in Excel. And I guess I don't even have to come up with this. There's a prepackaged test a hypothesis that Excel has that'll do this for me. Typically when we're working with small samples, the standard deviation is usually unknown. You can see that when I put the data into the spreadsheet, it calculates the sample size. It tells you the average, the sample mean, the sample standard deviation. Remember that formula I gave you for step 2 where we take X bar minus the hypothesized value? This is something that you have to add. You have to say this is what we want to test against. The standard error, the test statistic, all those numbers are plugged into the little formula. And so you're going to come down here, you're going to grab the test statistic right here. That's the second step. Whoops, let's see if I can cursor forward. There we go. The test statistic, t is equal to 1.225. Sometimes when I film, my animations get a little wonky. And so there's the first two steps. You come up with the test, that test that you came up with, the alternative hypothesis, the fact that we were testing against 2, that's what drives this number. You're going to have to always tell the software, this is what I want to test against, and then it calculates a test statistic based on that. And now you have a decision to make. Are you going to use rejection regions or p-values? And you can see the p-value information is given in the lower portion of the printout. The p-value information is right here. I'll come back and do the p-value approach in a second. But here, what if we were doing a rejection region? Well, I'm telling you to use alpha equal 0.10. So we start here. At alpha equal 0.10, we reject H naught if, and now you got to figure out what the answer to the if is, or what the end of the sentence is. And so in a two-tailed case, this is my t-table, I'm not going to put all alpha in that tail. I'm going to put alpha over 2 in both sides. So I'm going to put, what did we say earlier? I'm going to put half of that. That's supposed to be an alpha over 2. It doesn't look great. This is going to be 0.05 over on this side. This is going to be 0.05 over here. There's your 0.10. But now I have to find these cutoff points, this guy here and this guy here. And we're going to say reject if our test statistic falls further out in the tail. And so to find those values, I need a t-distribution. Oh, look at that. I guess I got lucky, right? So we're going to go, if we have 0.05 in the tail, I'm going to go to this column. I'm going to go to the 0.05 column. I'm going to go down. Our degrees of freedom is n minus 1. And so I'm going to go to the, let's see, there's 10 observations, so 9 degrees of freedom. And I'm going to match them up. And I see the 1.833. Now, this is going to disappear in a second, so I'm not going to write on top of this. 1.833. That's the value over here. Negative 1.833 is the value over here. And so you can see that's how I write my rejection region. We're going to reject the null hypothesis if our test statistic is bigger than 1.833 or less than negative 1.833, further out in the tails. So now let's get this t-distribution out of here, and let's remember what we actually have. 1.225, that's the test statistic. Where does that fall? It's going to fall about here, right? If this value is 1.833, the 1.225 does not fall in the rejection region, so our conclusion is at alpha equal 0.10, we fail to reject the null hypothesis. We can't reject. We would need to see a 1.9, a 2.0, a negative 3. We would need to see something further out in order to reject. So there's insufficient evidence to indicate that. When you reject, there's sufficient evidence. When you fail to reject, there's insufficient evidence to indicate that. And now how do I write it? Just go back to the problem. Copy and paste. The mean tree planting time for all medium-sized trees, that's the way we write mu, differs from 2 hours. We fail to reject. There's insufficient evidence to indicate that the mean tree planting time for all medium-sized trees differs from 2 hours. So we got our test statistic, our rejection region, and our conclusion. Only one step next or left. What's the assumptions? What are the assumptions we need? Well, assumptions, right now, where we're at in the class, there's only 2 assumptions you need to worry about. And one of them's easy. We always need a random sample. We need a random sample of tree planting times. We're going to need a random sample with everything we do. So a safe bet when I ask you for assumptions, which I will, make sure that the random assumption is there. The second assumption we need, and that's true whether you have a large or small sample size for assumptions. You need random samples regardless of the sample size. The second assumption that's necessary in this case, because we have a small sample, is that the population of X's needs to be approximately normal. And the population of X's is referring to, and the easiest way to say it or to think about it is, it's the observations. What's that? And you're obviously saying that's the value of 1.7. Yeah, but what is that? That's the time, the planting time. The population of all planting times, the labor times of planting all medium-sized trees, needs to be approximately normally distributed. The population of X's. Notice I'm not saying the mean needs to be approximately normal. That doesn't make any sense. It's the actual X's. The X's are the observations. The 1.7, the 1.5, the 2.6. Those are planting times. The population of all planting times needs to be approximately normal. And so as we're going through this test hypothesis, I want you to be able to do the 4 steps, but I'm always going to be asking about assumptions as well. So what changes if we do the p-value approach? Well, the p-value is the third step, right? The evaluating of the test statistics. So we're going to have the same null and alternative, mu's equal to 2, mu's not equal to 2. We're going to have the same test statistic of 1.225. In fact, the previous slide, is exactly the same. I haven't changed anything. What changes is our approach. And so let me go to the next slide, and we're going to do the p-value approach. Well, we have to take a look at what's the test. Well, the test we're conducting is a two-tailed. It's a not equal to test. And so we're going to go and grab the not equal to. We got to grab the p-value that applies to the test, or that coincides with the test we're conducting. You see I have three different tests here: lower tail, upper tail, and two-tailed. We're going to take the two-tailed p-value. The p-value for our test is 0.2518, given to us on a printout. And so now we make a conclusion. We got to compare two things. Last time with the rejection region approach, we compared the test statistic to the critical value. We compared the 1.225 to the, what was that number, 1.833. Here we compare a p-value to alpha. And so we got to go back. What's our alpha? Well, our alpha is 0.10. Is that value low? Is 0.10 low? Lower than, oh, I should have said it wrong. Is that value, is the p-value low? Is the 0.25 lower than alpha? No, it's not. It's high. P is high. What do we do when P is high? We fail to reject. There's insufficient, and you see the wording's exactly the same. There's insufficient evidence to indicate the mean tree planting time of all medium-sized tree differs from 2 hours. You can see that the assumptions are exactly the same. There's no difference in the way we say our conclusion. There's no difference in the assumptions. There's just a difference in our approach. The rejection region approach, you got to go to the table and find the cutoff points, a critical value. Once you get those critical values, you compare it to your test statistic. The p-value approach, you get the p-value. Now, sometimes, again, large samples, I may ask you to go and find it, but usually they're given on a printout. And I hope you're beginning to see that the p-value approach is a little bit easier. And sometimes when I ask students, which approach do you like? They give me the right answer, p-values. Everyone should like p-values. It's easier, it's better, it's faster, it's quicker, it's stronger, it's all that good stuff. But when I ask why, sometimes they give me an answer that's technically not correct. They say, I like p-values. And I'm like, so do I. Why do you like p-values? And they give me this answer: because there's no table involved. And if you think about what we just did with the rejection region approach, I brought the table in, we looked at the table, and then the table slid out. It's like, okay, here comes the table, there goes the table. And so it's obvious that the table's involved with the rejection region approach because I'm responsible for it, or you're responsible for it. With the p-value approach, it's like, well, I don't see a table, but the table was used. All these numbers were used, or use the table to come up with these p-values. The difference is the software uses the table. The software takes responsibility for the table. So when I ask the question, which do you like better? And you say p-values, as my dog is going crazy in the background, and you say p-values, there is a table involved, but you like p-values better because the software is doing the table work for us. Both of the conclusions are going to be the same. You're always going to make the same conclusion, whether you use rejection regions or p-values. A lot of times it's your choice. Sometimes I'm going to force you to use rejection regions, but more often than not, you're going to get that choice. If you're smart, if you're wise, you'll choose p-values. So take a look at some other examples of small sample test hypothesis. Make sure when you do, you have a printout available that has the test statistic on it. And when you have questions, or if you have questions, you know how to find us. Good luck.